We're going to talk a little bit more about testing endpoints and kind of summarize where we are and maybe do some practice problems. So intervals of convergence. How do we find an interval of convergence for a power series? First, we're going to start with the ratio test, and we'll find the values of x for which the series converges absolutely. Usually, this is going to be an open interval, a finite open interval centered at x equals a, the center of our series. Sometimes it will converge for all x. Once in a while, it will converge only at x equals a. Now, the only exception to starting with the ratio test is if we recognize that it was a geometric series, then it's really simple and straightforward because we know that a geometric series converges for the absolute value of r less than 1 and diverges everywhere else. You don't have to even check the endpoints, but that's more the exception than the rule. 99% of the time, we're going to start an interval of convergence question by using the ratio test. If the interval of convergence is finite, then we have to test for convergence at each endpoint. The ratio test, remember, fails at the endpoints. That's where it's inconclusive, because the endpoints come from where that limit as x goes to infinity of the n plus first term over the nth term is equal to 1. So we know that it's going to converge inside the interval. We know it's going to diverge outside the interval from the ratio test. The only thing we don't know is what's going to happen at the two endpoints. And that's where we have to do something else. And so that's where we're going to use our direct comparison test, the limit comparison test, the alternating series test, the p-series test, or the integral test. There's really no need to use the geometric series at this point because we hopefully would have recognized that right from the get-go. Okay, and we also know the series diverges outside of that interval for absolute value of x greater than r. So let's do some examples here where we're going to go through the whole process because it is pretty involved. So here's our power series. Notice it's got the x's in it. That's what makes it a power series. And so it's all this stuff. So we want to find the interval of convergence. So we will start by using our ratio test. So we're going to take the limit as n goes to infinity of the n plus first term over the nth term. Now, because it's an absolute value, that negative 1 to the n plus 1, we can just drop it because we don't care about the alternating signs. So we're going to have x to the, now when we plug in the n plus 1, that 2 times n plus 1 is going to be 2n plus 2. So there is our power of x. And likewise, we're going to have a 2n plus 2 in the denominator. And then we're going to divide by the nth term, so we'll get a 2n and an x to the 2n, and we want that to be less than 0. So we're going to, I like to write that and rearrange it. You don't have to do it this way, but I'm going to put the x to the 2n plus 2 over the x to the 2n, and we'll write the 2n over the 2n plus 2. And again, we want this to go to be less than 1. So these will cancel out, and as n goes to infinity, as n gets bigger and bigger, that plus 2 becomes insignificant. It's going to look more and more like 2n over 2n, which is going to be just 1. So what we're getting then is going to be this x squared is less than 1. So in this case, because that x squared is always going to be positive, we don't really have to worry about the negative. So we're going to get that x is going to be between negative 1 and 1. Now, we know our radius of convergence is 1, but we're looking for the interval of convergence. So our ratio test gives us the body of it, that inside the interval, but it cannot determine what's going to happen at the endpoints. So we are now going to look at each of the endpoints one at a time. So when we plug in the 1, x is 1, then we can see that this 1 to any power is going to be 1. So our series is going to become negative 1 to the n plus 1 times 1 over 2n. And n is going from 1 to infinity. So you may see that this is going to be an alternating series. So I don't think we can show this is going to converge absolutely, because I'm looking at it and thinking that if we ignore the alternating part, that's going to look like 1 over 2n, and we know that's really going to be a half times 1 over n, and that's going to be our divergent harmonic series. So I don't think we're going to get absolute convergence, so I'm just going to go straight for the alternating series test. So we can say the series alternates. We can say that the 1 in absolute value, the n plus first term, which is 1 over 2n plus 2, is less than or equal to 1 over 2n, so the series is decreasing, and that the limit as n goes to infinity of that 1 over 2n is indeed going to be 0. So by the alternating series test, the series converges. So we have now moved to including that right endpoint at x equals 1. So now our interval looks like we're including the 1. Now we still have to test the left endpoint. So now we're going to let x be negative 1. So now this thing is going to look like, let's see, we have negative 1 to the n plus 1. When we plug in negative 1 for the x to the 2n, we can think of that x to the 2n as being squared and then to the n over our 2n. So we can see that that negative is going to get squared out, and so that's just going to be 1 to the n, which is just 1n, or just 1 rather. So again, our series is going to look like negative 1 to the n plus 1 over 2n, which is identical to the one that we just did. So we don't have to repeat that. Also, by the alternating series test, this series converges. That is the series when x was equal to negative 1. So that means our final answer is going to include both endpoints. So there is our interval of convergence. I know it seems really crazy that you do the same amount of work for each of the endpoints that you do for finding all of the rest of them in the interval. So going from a radius of convergence question to an interval of convergence question essentially multiplies the amount of work by 3. I know, it's kind of crazy. Okay, let's look at our next one. So here is our series, and again, we're looking for the interval of convergence. As usual, we're going to take the limit as n goes to infinity of the n plus first term. So that's going to be 10x to the n plus 1 power over n plus 1 factorial. So we're using our ratio test, and we're going to get an n factorial and a 10x to the n, and we're interested in where that is going to be less than 1. So we can, again, I'm going to write this as the limit as n goes to infinity, and we're going to have the 10x to the n plus 1 over 10x to the n, and we're going to have an n factorial over an n plus 1 factorial. So we can cancel all but one of those 10x's. We'll recognize our n plus 1 factorial as n plus 1 times, times n factorial, and cancel the n factorial part of it. So we're going to get the limit as n goes to infinity, and now we're down to 10x over the n plus 1. Now, remember, we get to pick an x first. Once we pick that x, it stays fixed, and then we let n go to infinity. So no matter how big an x we pick, as n goes to infinity, that is going to go to 0, which is less than 1. So what we're going to get is that this will converge for all x. So that is our radius of convergence is infinity. Our interval of convergence is negative infinity to infinity. Okay? Well, let's try another. So again, we start with our ratio test. So we'll get good at this ratio test because we're going to get so much practice at it. We're going to get our n plus first term. So I'm going to write that with the n plus 1s over our nth term, which is going to look like that. And we're interested in where that is less than 1. So we can see that all but one of those powers of x plus 1 are going to cancel. Our n plus 1 factorial we are recognizing as n plus 1 times n factorial. So this is going to become the limit as n goes to infinity, and it looks like we have an n plus 1 and an x plus 1. And we're hoping to get that to be less than 1. But remember, again, we pick a value for x. Once we choose it, it stays fixed. And then the n is going to go to infinity, which means this is going to blow up and go to infinity for any choice of x except for negative 1. So we will say this converges only for x equal to negative 1. That is our interval of convergence. And remember, our radius of convergence is 0 in this case. All right, one more example here. So we, again, are going to start with our ratio test. So the limit as n goes to infinity, we're going to go x minus 3 to the n plus 1 over 2 times n plus 1 is going to be 2n plus 2. And then we have 2n over the x minus 3 to the n. And we're trying to find where that is going to be less than 1. So those are going to cancel. The 2n over 2n plus 1 as n goes to infinity is going to go to 1. So we're going to get our limit as n goes to infinity. And all that's left is our, what do we have left? Just the x minus 3, I think, which we want to be less than 1. So that means we're going to, we can see our radius of convergence is 1, but we want the x minus 3 to be in between 1 and negative 1. That's what this absolute value of x minus 3 less than 1 means. Since we're looking for the interval of convergence, we're going to add 3 to both sides, and so we will get that 2 is less than x is less than 4. So this is where we stand after the ratio test, but we don't know what's happening yet at the endpoints. So we're going to test them. So let's see what happens when we put in 4 for x. So back in our original, when we plug in 4, we get 4 minus 3 is 1. 1 to the n is 1. So this becomes 1 over 2n. So you may see that this is really 1/2, if you factor it out, times 1 over n, which is the convergent, or the divergent, rather, harmonic series. So if the harmonic series goes to infinity any constant times that will also go to infinity, so it diverges. So that means we are not going to include x equals 4 in our interval of convergence. So now we're going to look at the left endpoint. So now when we plug in 2, our series now becomes 2 minus 3 is negative 1 to the n over 2n. So you may recognize this as it's going to be an alternating series. So we're going from 1 to infinity. So if you want to write out a few terms, you don't really have to, but negative 1 to the first is negative 1 over 2. And then negative 1 squared is positive. Plugging in 2 will be 1/4. And then minus 1/6, and on and on and on. So we can see that the series alternates. And we can see that 1 over 2n plus 2 is less than or equal to 1 over 2n. So the terms in the series decrease, and we can see the limit as n goes to infinity of 1 over 2n is 0. So we can conclude by the alternating series test, the series converges. So we end up with, at the end of the day, we're going to include that left endpoint, but not include the right endpoint, and that is our interval of convergence. So let's pause a moment here and kind of reflect at where we are. I've thrown a lot at you in the last few days. So here in the white are going to be all of our various tests for convergence and divergence. I think making like a note card is really helpful so that you can look them over and kind of see them, say them, at least in your head, if not out loud, so that they become just part of your repertoire, and that you can not forget any, because inevitably that's the one that you're going to need. So we have, for tests of convergence and divergence, are the nth term test. Now remember, that only proves divergence. So we know that if the limit as n goes to infinity of the nth term goes to something other than 0, it's going to diverge. But if the limit as n goes to infinity is 0, that means nothing. We don't know that it's going to converge. It still may diverge. The geometric series is nice. It doesn't come up a lot, but it does come up regularly, and that's particularly powerful, and you can appreciate it more now because it's conclusive. When we can tell, first of all, is it going to converge or diverge, because if the absolute value of r is less than 1, we know it's going to converge, and if the absolute value of r is greater than or equal to 1, we know it's going to diverge. And furthermore, we know the interval of convergence will never include the endpoints. It's just going to be the absolute value of r less than 1. And in a very rare case, I mean, it's not very often that we can get beyond the convergence question. In the case of a geometric series, we can actually find what the sum is if that series converges, because its formula is s equals a over 1 minus r, and you'll be expected to know that because that can be asked. Then we have the direct comparison test. Doesn't typically tend to be a favorite because you have to be very careful in saying that your terms are less than a convergent series or greater than a divergent series, and you have to be very careful in that inequality. The ratio test is going to be a favorite. It's going to become one that we use so much, it just becomes the one we probably feel the most confident in. The integral test is not used often, but you can't forget it because you will see some series, and that's going to be the only way you can figure out if it's going to converge or diverge. The p-series test is great because it is so user-friendly. I personally like the limit comparison test because I think it's way easier to use. It's more forgiving than the direct comparison test, where you have to very carefully state that your series is less than a convergent series or greater than a divergent one. With the limit comparison test, it's just, let me just see what it acts like in the big picture. If the limit of our series over the comparison series goes to a constant, we know they're going to act the same, and we don't sweat the details. The alternating series test is a nice one. You just have to remember that you have to state those three conditions are met. We sort of have another one, the telescoping series. That doesn't come up very often, but and it's usually pretty obvious when you need to use it. But it will probably be used the least of all of those. We have 4 different error bounds. We use the geometric series some, not a whole lot. The alternating series error bound and the Lagrange error bound are by far the ones that get used most. And of course, everybody likes the alternating series bound because it is so simple to use. The error is less than or equal to the absolute value of the next term. The Lagrange error bound is much more complicated, at least for students when they're starting out. It's a little bit mysterious, but it's one we're going to have to just continue to work on and get more comfortable with. Very rarely we can use an integral as an error bound. I just include it there, so it's a possibility, but very, very seldom. All right, very good.